All the earthquake science in the world doesn't mean a thing if it can't actually save lives. So today, that's exactly what we're going to do. We're going to bridge that gap and look at how we can go from feeling totally powerless against earthquakes to being powerfully prepared.
So let's just get right to it. Can we predict earthquakes? I mean, this is the question, right? It's the one everyone asks. It's kind of the holy grail of seismology, and it really frames everything else we're about to talk about. The answer, well, it might not be what you expect, but it's absolutely key to understanding how we actually keep ourselves safe.
All right, here's how we're going to break it down. We'll start with that prediction problem. Then we'll dive into mapping the shaking, getting a few seconds warning, why building to survive is so critical, and finally, we'll get into your personal prep plan. Okay, let's dive right into section 1, the prediction problem. This is all about that search for the holy grail of seismology. For decades, right, scientists have been trying to find a foolproof way to know exactly when and where the next big one is going to hit. But it has turned out to be one of the toughest nuts to crack in all of science.
Okay, so this is where we have to get really clear on our terms because it's super important. There's a huge difference between prediction and forecasting. When we say prediction, we mean pinpointing the exact time, place, and size of a quake. And right now, that's just not achievable. But forecasting, that's a different story. That's about calculating the chances, the probability of a quake happening in a certain area over decades. And that's a well-established science. It's the bedrock of everything we do to get ready.
So you might be wondering, why is this so hard? I mean, we've all heard the stories, right? Animals acting weird, radon gas leaking from the ground. But the truth is, none of those methods have ever held up under serious scientific testing. The real issue is, an earthquake starts as a chaotic system, literally at a nanometer scale. It's a tiny, tiny shift deep in the earth that could either just fizzle out or it could cascade into a massive rupture hundreds of kilometers long. A tiny difference in those initial conditions, something we can't even measure, leads to completely different outcomes. It might just be physically impossible to ever predict them with perfect accuracy. Okay, so if we can't predict, what can we do? We forecast. And that brings us to our next section, mapping the shaking. This is where we use science to look at the long-term risk. Think of it as our first and maybe most powerful tool. It gives us the big picture we need to prepare smartly. And this is how we do it. This is a seismic hazard map. Now remember, it's not a prediction map. It's a probability map. It's a tool that pulls together everything we know, where the faults are, what past earthquakes were like, the local geology, and it estimates how hard the ground is likely to shake at any given spot. This map is the absolute foundation for modern building codes, for setting insurance rates, for all kinds of crucial infrastructure design. So how do we actually use a map like that? Well, it all comes down to a number, 2%. Engineers have a standard. They design our modern buildings to be able to withstand the level of shaking that has a 2% chance of happening in any 50-year period. Now, 2% in 50 years might sound like a tiny risk, but what it actually represents is a very strong, pretty rare earthquake. And here's the key. The goal isn't to make buildings earthquake-proof so they don't get a single crack. The goal is to prevent them from collapsing. It's all about saving lives. All right, so we've talked about the long-term forecast, but what about right when it's happening? This brings us to our next section, a few seconds warning. This is where technology races against the shaking itself. We can't predict a quick days out, but we can now get a warning in those crucial seconds after it's already started, but before the really bad shaking gets to you.
So how on earth is that possible? It's basically a race. You see, an earthquake sends out two main types of waves. First, you have the P waves. They're fast, but they're not very damaging. Think of them as the little rumble. Then come the S waves. They're slower, but they're the ones that do all the damage, the real destructive shaking. The genius of an early warning system is that our sensors pick up that first, fast P wave. Then, an electronic alert, which travels at pretty much the speed of light, zips ahead of those slower, damaging S waves, giving you that critical warning gap.
And naturally, the more distance between you and the epicenter, the more warning time you get. So let's say you're about 50 kilometers away, you might get around 8 seconds. Double that to 100 kilometers, and your warning jumps to about 18 seconds. Get out to 200 kilometers, and you could be looking at 40 seconds of warning. And I know, 8 seconds, 18 seconds, it doesn't sound like a lot of time. But trust me, it can absolutely be the difference between life and death. Because think about what you can do in just a few seconds. It's incredible. Automated systems can slam the brakes on trains to stop them from derailing. In hospitals, surgeons can pause what they're doing. Fire station doors can pop open automatically so the trucks aren't trapped inside. And for you personally, It's enough time to do the one thing that will protect you most. Drop, cover, and hold on. But look, early warnings and forecasts are amazing tools, but they're only one part of the solution. That brings us to what is, without a doubt, the single most effective life-saving tool we have: building to survive. It really all comes down to the quality of the buildings we're in.
I mean, this quote really says it all, doesn't it? The difference between 100 deaths and 100,000 deaths is almost entirely due to building quality. We have to remember, earthquakes don't kill people. Collapsing buildings kill people. And whenever you see two quakes of the same magnitude hit different places, but with drastically different death tolls, you can almost always point to one thing: the quality of their buildings and their building codes.
And here's a perfect and frankly scary example: the soft story building. You know what I'm talking about. An apartment building where the ground floor is just a big open garage held up by a few skinny columns. That first floor is dangerously weak, and it's just asking to collapse in an earthquake. But the good news is we can retrofit them. We can go in and strengthen that structure and prevent a total catastrophe. The sad truth is, most deaths in earthquakes happen in older buildings just like this that just haven't been updated.
Modern buildings, on the other hand, use some seriously smart engineering to ride out the shaking. They're designed to be ductile, which just means they can bend and flex without snapping. Some even use what's called base isolation, where the whole building basically floats on these giant bearings that soak up the energy. Or they'll have massive dampers, which are like giant shock absorbers for the entire structure. The whole game is about finding ways to safely dissipate all that incredible energy the earthquake is throwing at the building.
And here's the kicker: strengthening our buildings isn't just about saving lives, which is obviously the most important thing. It's also an incredibly smart investment. FEMA has studied this, and the numbers are pretty staggering. For every single dollar we spend on retrofitting, we save anywhere from $4 to $8 in future disaster costs. It's a total no-brainer.
Okay, so we've covered the big science, the big tech, and the big engineering: forecasting, early warnings, strong buildings. But the final, crucial piece of this whole puzzle, that comes down to you. It's your personal prep plan. What you do is what will determine how you and your family get through the immediate aftermath. When the shaking starts, your mind might go blank, so you need to have this drilled into your brain. There is one simple protocol: drop, cover, and hold on. That's it. You drop to your hands and knees before the earthquake knocks you down. You cover your head and neck by getting under a sturdy desk or table, and you hold onto it until the shaking stops. Seriously, do not run outside. Do not stand in a doorway. That's a myth. This simple action protects you from falling objects, which is the #1 way people get hurt.
Okay, so what about after the shaking stops? You have to assume you'll be on your own for at least 72 hours, 3 days. First responders are going to be completely overwhelmed. So having an emergency kit ready to go is not just a nice little project for a weekend, it's an absolute necessity. You'll need things like water, food, a flashlight, first aid, the basics to get you through. And once that first big shaking stops, your job isn't done. First thing, check yourself and others for injuries. You have to expect aftershocks, they're a guarantee. And when they hit, you do the same thing: drop, cover, and hold on. And one more really critical point: if you are anywhere near a coast and you feel strong, long shaking, do not wait for a siren or an official warning. That shaking is the warning. Get to high ground as fast as you can to get away from a potential tsunami.
So there you have it. From the chaotic physics happening miles beneath our feet to the simple emergency kit sitting in your closet, the science is crystal clear. It gives us a path to go from feeling powerless to being prepared. We know what works. We have the tools: long-term forecasting, a few seconds of early warning, strong buildings, and a personal plan. The science is sorted. The only real question left is your plan ready?